Welcome back. This is Amit Sinha. Last time, forces learned to balance. Today, they learn to twist. We meet torque, find the true home of gravity, and uncover the physics of tipping over. Give me a place to stand, Archimedes is said to have boasted, and I will move the earth. He was not bragging about strength, he was bragging about geometry. A 2-meter crowbar rocking on a pivot 2 centimeters from its tip multiplies your push 100 times. No motor, no magic, just distances doing work that muscles cannot. And geometry can do stranger things than multiply. Watch a stack of ordinary books grow past the table edge, one careful shift at a time, until the top one floats entirely over empty air. It looks like a trick photograph. It is not. By the end of this lecture, you will know how to lean the stack out as far as you like. Here is the plan. First, what torque actually is. Then a small theorem with big consequences why you may take torques about any point you please. Then, where gravity truly grabs a body and the 2 ways things fall over. The problems, a painter on a plank, the leaning ladder, a tilting block, a hanging chain, and that impossible stack. Open a door, and physics opens with it. Push near the hinge, the door barely moves. Push at the handle, the same force, it swings easily. Now, push at the handle, but along the door, straight toward the hinge, nothing at all. Force alone does not decide turning. What matters is how much force, how far out, and in what direction. So we define the turning strength of a force, torque. In words, first, torque equals force times lever arm. As a formula, torque tau equals Rf sine theta, the distance out to where the force is applied, the force itself, and the sine of the angle between them. Push at the hinge, R is 0. Push along the door, sine theta is 0. The door already knew this formula. There is a second way to read the same product. Group R with sine theta. That combination is the perpendicular distance from the pivot to the force's line of action, the lever arm. Slide a force along its own line and its torque cannot change. Only the perpendicular missed distance counts. Torques about the same point add up, each push contributing its own turning strength. And the unit is newtons times meters. A torque of 1 Newton meter is a 1 Newton push at the end of a 1 meter wrench. Now the full law of standing still. Last lecture demanded the forces sum to 0. That stops the body's center from accelerating. But a wheel can spin without its center going anywhere. So equilibrium needs a second equation. The torques must also sum to 0. Forces balance and torques balance. Every statics problem, from here to the end of physics, is these 2 lines. There is a deeper way to write the definition, and it pays off immediately. Torque is a vector equal to R cross F, the cross product of the position and the force vectors. Its size is exactly Rf sine theta, the area of the parallelogram, the 2 arrows span. Its direction is the new information, perpendicular to their plane. That is the axis of the turn. Which way along that axis? Curl the fingers of your right hand from R toward F, and your thumb points along the torque. On a flat page, there are only 2 choices. Out of the page, drawn as a dot inside a circle. Into the page, drawn as a cross inside a circle. That gives our signs. Counterclockwise turning means the torque points out of the page, counted positive. Clockwise means into the page, negative. Watch the symbol flip as the force swings around the arm. In 2 dimensions, a torque is just a sign number, and torques add. The balance law is really a vector law. The sum of the torque vectors is 0. The torque equation comes with an anxiety. Torque is measured about a point. Which point? The hinge? The center? A corner? It sounds like each choice gives a different equation, and only one of them is right. The truth is better. For a balanced body, every choice is right. Let us prove it. Take talks about an origin O. Each force needs its position arrow, R1, from O out to the first force and R2 out to the second. Now pick a different pivot, P, and draw its own arrow, RP. Seen from P, every position arrow is simply the old one, minus RP. One subtraction, the same for every force. Expand the sum, and it splits in two. The first piece is the old talk about O. The second piece is the key. RP is one fixed arrow, identical in every term, so it factors clean out of the sum, leaving RP cross the total force. But the body is balanced, and the total force is 0. The second piece dies, and P agrees with O. Watch it live on the simplest balanced body there is. Two equal and opposite forces. F up on the right, F down on the left, a distance, D apart. Slide the pivot anywhere you like, inside the body or beyond it. Both lever arms change, but their difference never does, and the readout stays stuck at FD. Now drop the pivot right onto one of the forces. Its lever arm collapses to 0, and it vanishes from the ledger, leaving one force and one arm, FD, in a single line. That is the working move of this entire lecture. An unknown force contributes nothing about a point on its own line of action. Choose the pivot that kills the unknowns. Next question. Where does gravity act? On a point mass, obviously at the point. But a plank, a ladder, a body, gravity tugs every atom separately. Millions of little parallel pulls. Can we replace the swarm with a single arrow? And if so, where does it stand? Take talks about the origin. Piece 1, with mass m1 at distance x1, contributes m1g x1. Piece 2 contributes m2g x2, and so on down the line. Sum the pieces and factor out g. The sum that remains, mass times position, added over all pieces, is exactly the recipe that defines the center of mass. So the total torque is the full weight, mg, acting at that single special point, xcm. The same is true of the force itself, and the whole swarm collapses, one arrow, magnitude, mg, planted at the center of gravity. And nature hands you a way to find that point without integrals. Hang the body from a pin and let it settle. The center of gravity swings directly below, so a plumb line through the pin crosses it. Hang from a second point and repeat. The two lines cross at exactly one spot, the center of gravity. From now on, every plank and ladder wears its whole weight there. That promised proof delivered. Armed with torque, we can finally split a question that friction alone could not answer. When a tilted object lets go, does it slide or does it topple? These are different failures, each with its own physics. Sliding we solved last time. The block slips when the pull along the slope beats friction's budget, tangent theta greater than mu s. Tipping is torque's business, and it hides inside the normal force. On level ground, the surface pushes up all across the base. Tilts the surface, and that support migrates downhill. The pressure crowds toward the lower edge. The normal force's line of action slides toward the corner. Why? Because N must do two jobs at once. Cancel the into slope part of gravity and cancel gravity's torque, and it can only do the second by shifting its line of action. When the support reaches the corner, N has no farther to go. One more degree of tilt, and gravity's torque about that corner is unopposed. The block rotates, it tips. The threshold is pure geometry. The block tips when its center of gravity's plumb line falls outside the base. Tangent theta equals W over h, width over height. No mass, no friction coefficient, just the shape. So the tilted block runs a race between two thresholds, slide at tangent, theta equals mu s, tip at tangent, theta equals W over h. Whichever is smaller is reached first, and that failure wins. Material against geometry, we will stage the race properly in the problems. Now let's get to work. A painter's plank, mass M, rests on two supports, one at its left end, one short of its right end, leaving an overhang. The painter, mass MP, walks out along the overhang, one careful step at a time. The plank does not slide, it will fail by tipping. How far past the support can she go? The cast of forces, the plank's weight. mg at its center, the painter's weight. mpg under her feet. And two normal forces, na at the left support, nb at the right. Two unknowns, but we now own two equations, forces and torques. Now the move. Take torques about the right support. B, NB acts there, gone before we start. And the tipping signature is hiding in the other support as the painter walks out. The left support carries less and less. Tipping begins at the instant. NA reaches 0 when the plank is just about to leave the left support. At that instant, only two torques about B survive. The plank's weight, a distance c to the left of B, turns it one way. The painter, a distance x to the right, turns it the other. Balance them. mgc equals mpgx. G cancels, and the last safe state is x max, the mass ratio, m over mp, times c. Numbers. A 30-kilogram plank, its center 1 meter inside the support, a 60-kilogram painter, x max equals 30 over 60, of a meter, barely half a meter of safety. Watch NA die as she walks. The arrow shrinks, hits 0, and the plank pivots. And check the limit. A painter standing right over the support can never tip it. The formula agrees. Now for the classic, the leaning ladder. A uniform ladder of mass M and length L leans against a smooth, frictionless wall, its feet on a rough floor with coefficient μs. Lean it too shallow and it skids out. What is the minimum angle? Theta, measured from the floor at which it stands. 4 forces. The weight mg at the middle of the ladder. The frictionless wall can only push perpendicular to itself, a horizontal nw at the top. The floor pushes up with nf, and friction F holds the feet, pointing toward the wall, fighting the skid. Forces. First, vertically, the floor carries everything. Nf equals Ng. Horizontally, only two players. Friction must cancel the wall's push. F equals Nw. Two equations, three unknowns. The missing third equation is torque. Take torques about the feet and watch the choice pay. Nf and F both act there, so both vanish. Two torques remain. The wall's push acts a height, L sine theta up, and turns the ladder into the wall. The weight acts a horizontal distance, L over 2 cosine theta out, and turns it away. Set one against the other, and there is our third equation. Solve for the wall's push, Nw equals mg over 2, cotangent theta. Friction must match it, and friction is capped at μs nf, which is μs mg. So mg over 2 cotangent, theta at most μs mg, the mass cancels and the condition falls into one line, tangent theta at least 1 over 2 μs. Now send a climber up, mass mc, partway along. Redo the torque about the feet. Her weight adds a torque that grows as she climbs. The wall pushes harder, so friction's demand grows in step, while its budget, μs, times the total weight, stands still. Demand climbs a straight line toward the ceiling. The dangerous moment is the top of the climb. Numbers. Rubber feet on dry wood give a friction coefficient near 0.5, so the bare ladder needs tangent, theta at least 1. That is 45 degrees. And notice the design lesson, steeper is safer, which is why fire crews stand ladders at 75 degrees and why ladder feet wear rubber shoes. Buying friction buys angle. Now the race, run honestly. A block W wide and H tall rests on a plane we tilt slowly, so slowly it is always in equilibrium until something gives. Slide and tip are both waiting. Geometry will decide which one arrives first. The slide threshold we own from last lecture. Friction's budget runs dry at tangent. Theta equals μs, the blue tick on the gauge. As the table tilts, the needle crawls toward it. The tip threshold we built today, the center of gravity's plumb line, reaches the downhill corner when tangent. Theta reaches W over H, the goal tick. 2 ticks on one gauge, 2 different alarms. Run it. A tall, narrow block, W over H, is small, well under μs. Tilt, and the plumb line wins the race. The block tips over while friction still had budget to spare. Tall things topple. Reset with a short, wide block. Now W over H is large, and μs is the smaller number. Tilt. Friction's budget runs dry first, and the block slides away intact. Squat things skid. One picture holds every case. Axis μs across, W over H up. The diagonal line μs equals W over H splits the plane. Above it, blocks slide first. Below it, they tip first. Before you tilt anything, its shape and its surface have already voted. A filing cabinet and a hockey puck live on opposite sides of one straight line. The derivation centerpiece. Hang a chain, linear density, lambda, between 2 posts, and let it settle. What curve is that sag? Galileo said. A parabola. It looks like one. It is not one, and the difference is a lesson in how curves are born. We will ask the chain itself. The chain is not rigid and not massless, so we reach for last lecture's sharpest tool, the element. Slice out a tiny arc of chain and look hard at its 2 cut ends. Between one cut and the other, everything drifts, the pull grows a little, and its direction tilts a little. The slide marks both drifts, and the slice's own weight hangs below. Balance the slice horizontally. Nothing else pulls sideways, so the horizontal parts of the 2 end pulls must cancel exactly, drift and all. That forces one combination, t cosine theta, to come out the same at both cuts and therefore the same everywhere along the chain. Call that constant. T0, the horizontal pull, set once by how hard the posts are pulled apart. Vertically, the slice must carry its own weight, so the 2 end pulls cannot cancel. The right cut pulls up harder than the left by exactly the slice's weight. Read the denotation that way, the value at the right cut minus the value at the left. The change in t sine theta across one slice equals lambda g ds. Now, let the constant do the work. Multiply and divide the vertical component by cosine theta, and the protected combination appears on its own, t cosine theta, which is T0. The varying tension drops out of the problem entirely. What survives is a constant times tangent. Theta. Pure geometry. And tangent, theta is an old friend. The tension points along the chain, so theta is the angle of the curve itself, and the tangent of a curve's angle is its slope. Substitute, and the vertical balance turns into a constant times the change in slope equals the slice's weight. The constant slides straight out of the differential. That is exactly why we hunted it first. One last trade, a step of arc length for a step of horizontal run. Pythagoras prices the exchange at root 1 plus slope squared. And there it is, a differential equation whose unknown is not a number but a whole shape. Solving it is next. Substituting u for the slope, dy by dx, and a for t0 over lambda g, the whole equation collapses to one clean line. Du over the square root of 1 plus u squared equals dx over a. A carries units of length, and it will be the whole personality of the curve. Slope on the left, position on the right. Integrate. The left integral is a classic, and its answer is the inverse of the hyperbolic sine. So the slope is u equals sinh of x over a. Integrate once more, and the hyperbolic sine lifts to the hyperbolic cosine y equals a. Cosh of x over a. That is the curve the chain was drawing all along. And a earns its keep, t0 over lambda g, horizontal pull over weight per meter. Pull the posts hard, a grows, and the curve flattens. Let the chain go slack, a shrinks, and it plunges. One length rules the entire family of shapes. The curve has a name, the catenary, straight from the Latin for chain. Galileo missed it, but others such as Bernoulli, Leibniz, and Huygens nailed it within a year of each other. You have just walked their derivation. Now look up, because the catenary is everywhere. Every power line between two pylons, every chain fence, every mooring line drooping between ship and dock, gosh, drawn at civic scale. Even a spider's silk, sagging under dew, runs the same equation with a far smaller a. Numbers. For a feel. A chain spanning 30 meters between equal posts, with a equal to 45 meters, sags about 2.5 meters in the middle. Halve the horizontal pull and the sag roughly doubles. Linemen tension cables by exactly this arithmetic, reading sag with a surveyor's level. Now turn the whole thing upside down. A hanging chain carries pure tension along its length. Flip the curve, and tension becomes pure compression along the arch. No bending anywhere, every stone pressed straight into its neighbors. That is why the Gateway Arch in St. Louis is a flattened catenary, 630 feet of cosh standing in steel. So the element method has now built two curves for us. Wrap a rope around a post, and it grew the exponential e to the mu theta. Hang a chain in gravity, and it grew a cosh. Same slice, same balance, different geometry. Heed the tool, it is not done. The last problem is the stack from the opening, and the trick is to think from the top down. One book first, it balances as long as its center of gravity stays over the table, so it can overhang by half a book length, L over 2, and not a hair more. Now, the beautiful move, induction. Suppose the top k-1 books are already leaning as far as they dare, and their collective center of gravity hovers exactly over the right edge of book k. The whole tower above is balanced on that single edge. The question is how far book k itself can slide out over book k plus 1. Set up coordinates. Put x equals 0 at the right edge of book k plus 1 and call dk the distance book k pokes past it. The tower above contributes its center of gravity at dk. Book k contributes its own center, half a length back, at dk minus L over 2. Combine them. K minus 1 shares at dk, 1 share at dk minus L over 2, all divided by k. At the verge of tipping, this combined center sits exactly at 0. Clear the fractions, and k dk equals L over 2. So the kth book from the top may overhang by L over 2k. Exactly. Every level obeys the same little law. Now, add the steps. The total overhang after n books is L over 2 times 1 plus 1 half plus 1/3 and onward. The harmonic series, a sum of shrinking but stubborn terms. Does it settle or grow without bound? Compare it with a curve. Each term, 1 over k, is a bar of area. 1 over k and the bars together enclose the curve 1 over x. So the sum beats the integral of 1 over x, and that integral is the logarithm of n plus 1. The logarithm grows forever. Slowly, achingly, but forever. 4 books already overhang more than one full length. 31 books by 2 lengths. 227 by 3. Unlimited overhang at an ever crueler price. That is the photograph from the opening. Explained, no glue, no trick, just centers of gravity parked, each one exactly on an edge, all the way up. Physics allows a staircase into thin air. It just taxes every step on a logarithmic schedule. The 30-second audit. The ladder, μs to 0, and the minimum angle climbs to 90 degrees. On perfect ice, only a vertical ladder stands, which is no ladder at all. Correct. The plank, put the painter directly over the support. X equals 0, and no finite mass can tip it. Correct. The block, W over H huge, a flat tile, tipping would need the plumb line to clear an impossibly wide base, so it can only slide. W over H tiny, a standing pencil, it tips at a whisper of tilt. Both match daily life. And the catenary, pull the posts hard, so A dwarfs the span. Tailor the cosh, 1 plus x squared over 2 a squared. A parabola. Galileo was not foolish. He was looking at taut chains, where the true curve hides inside its own first approximation. Every limit lands. The audit stays free. 3 ideas to carry forward. Equilibrium is 2 laws, not 1. Forces, balance, and torques, balance. And the second is where shape enters physics. The pivot is yours. Choose it where the unknown forces act and they never enter the ledger. And failure is a race. Slide against tip, budget against geometry, and the lower threshold always collects. The habit for every rigid body from now on, before you write a single talk, stop and choose the point that makes the most unknowns disappear. 1 second of choice saves a page of algebra. Next time, things finally get moving. F equals ma, handle properly what Newton's laws actually claim. Free body diagrams as a discipline, and machines built from rope and pulley. A double Atwood machine with a surprise hiding in its effective mass, a wedge that accelerates out from under its own block, and a painter who hoists herself by her own pulley. Statics is over. Dynamics begins. That wraps up this lecture. This is Amit Sinha. Thanks for watching the Sinha Foundation channel. See you in the next one.